Hello everyone, my name is Kazuho Oku. Today I'd like to talk about evolution of Internet protocols. I'd like to introduce QUIC, which is the new transport protocol, and HTTP3, which is the HTTP binding for QUIC. Let me introduce myself. I am Kazuho Oku. I am lead developer for H2O, which is a HTTP server of open source. I work at a company called Fastly, which is the company which uses the H2O as reverse proxy. As I develop H2O, I also contribute to IETF, the standard body. For example, RFC 8297, which is to improve the speed of HTTP, and also to improve the privacy of TLS to extend the ESNI, which is renamed as ECH. I was a co-author for that. And also for HTTP2 and HTTP3, the new priorities, which is the extensible priorities, I was also a co-author of the extension. Now let's talk about the current status of HTTP3. HTTP3 is HTTP on QUIC. Protocol design is finished and draft is under final review. Already it's being operated and utilized, so in the case of Google Chrome, already 25% of the users have HTTP3 enabled if the servers are enabled. Also, Facebook has unique client app. And when the HTTP3 is enabled with the client app, 75% of the internet traffic is now switched over to HTTP3. Toward the end of year and early next year, we expect that HTTP3 to be more common. Now, why were the HTTP3 and QUIC born? Let's first look at the transport protocol before the QUIC, that is TCP. Now, TCP is the transport protocol which was the basis of Internet. In 1981, it was established, so that's about 40 years ago. TCP combines IP packets and provides the bidirectional, reliable byte stream. It detects the loss of the IP packets and retransmits it, so it has the loss recovery. Also, depending on the network congestion, the transmission speed is adjusted, so it does the congestion control. So this TCP protocol has been utilized for about 40 years as a basis of Internet and web. Now, talking about web, we have been trying to speed up the web. On application layer, we worked on minimizing the file that is called minify, and also on the HTTP layer, we used the cache to reduce the number of requests. In 2015, the HTTP2 was established so that we can effectively utilize network bandwidth. In 2018, TLS 1.3 was established to reduce the handshake latency. But transport continued to be TCP. Why was that? Were there not issues with transport TCP? Now, let's look at the benchmark results of HTTP2. This was announced by Human Bestie, my colleague, in 2016. This is a simulation when we show a web page which is faster, HTTP 1 or 2. When 2 is faster, the green is shown. When 1 is faster, it shows red. On the left, this is without the packet loss. On the right, we are showing with 2% random packet loss. Now, without the packet loss, HTTP2 is fast. But with 2% random packet loss, 2 is not necessarily faster than 1. And this is a simulation, so reality has some room for discussion. But we can say that the HTTP2 is not almighty. One of the issues behind this is head of line blocking. when there is a preceding packet which is lost, succeeding packet cannot be utilized even when the succeeding packets have arrived. TCP is byte stream, so when there is a preceding packet lost, the succeeding packet cannot be utilized. In HTTP2, the multiple requests share one TCP connection. So when there is one packet loss, the lost packet needs to be transmitted and recovered in order for the all response to proceed. So this is a major impact. Next, let's look at the latency before the connection establishment. With a TCP, when first client sends SYN packet and the server receives the SYN and returns it. So this is received by the client. This is one round trip. And then there's a TCP handshake. So there are two round trips. So TCP and TLS. Can we not do this simultaneously? If we can do it, there can only be one round trip. So that was the second issue of TCP. Of course, various efforts have been made. TCP Fast Open is a good example. This is for Linux, Apple, and Windows. We are having a lot of operating systems. But for 80% of the network, this works. But for 20%, it does not work. So why does it not work? TCP Fast Open, this is a protocol extension. There's a firewall who thinks that this behavior is skeptical. TCP should not move this way. This must be an attack. So disconnect is done. So because of this firewall, TCP Fast Open operation is still difficult. So TCP Fast Open is not widely utilized, and this firewall issue continues. So this is chicken or egg situation. So when the ecosystem is too optimized based on the existing behavior, so-called ossification occurs. So ossification occurs due to this. And the fourth issue is the extension of the TCP function takes time. TCP Fast Open that I talked about earlier, it took 4 years to enable the major operating system. And also there has to be time for the users to upgrade. So with one functional addition, it takes a long time. So it's very difficult to repeat the new experiments and find a new method. So ossification issue, you have to really test it. So if one experiment takes several years, it's very difficult to realize. The last issue is parking lot problem. So as you see in this diagram, a person is using Wi-Fi at home, but she goes out and it switches over to 4G network. In TCP, the connection is cut off once. When you use the big cities in Japan, people would walk out of the home, but in the United States, people drive. So this is why this is called parking lot problem. So as the network is switched over, this telecommunication continues, and it's called migration. And there is one issue or one thing we have to be concerned about, that is user tracking. That is to say that when you can monitor the connection over the multiple network for a long time, you can find out if this person is at office or at home or have gone to different unusual place. So not at the transport level, but using the iPhone push telecommunication, using the TLS client certificate, the user tracking was possible. And to resolve that issue, TLS 1.3 was established. So those are the issues that we need to resolve. But the ossification and change of function of the telecommunication stack will take time. So those were the issues with TCP.
That's when development of QUIC started. QUIC started as a Google Chrome experiment, as an UDP-based HTTP protocol that was deployed on Chrome. Google's QUIC, the so-called GQuic, had a unique encryption and handshake protocol. Since then, based on Google's proposal, IET have decided to standardize QUIC. Instead of making it dedicated to HTTP, they have decided to rebuild QUIC as a general-purpose transport protocol like TCP and decided to use TLS 1.3 as the handshake and encryption-based technology and make QUIC just as secure or more secure protocol than TLS. Also decided to port HTTP2 onto QUIC as direction. Since then, over 4 years, 13 IETF meetings and 11 interim meetings were held, and 450 pages of specification draft was developed. In the process, 1,900 GitHub issues and 2,400 pull requests were opened. Had discussions like this. You see many people queuing up for the mic. Had discussions like this. This is an interim meeting held in Paris. We brought deployments together and tested compatibility like this. What did we discuss? How is transport protocol being designed? In standardizing QUIC at IETF, what do you think was the first debate? It was the endian debate. You can't avoid designing an encode. GQuic was little endian, but on the other hand, IETF protocol traditionally used big endian, so that's why it developed into a debate. Which would you choose? As a result, what happened was that neither big nor little were chosen. They have decided to use variable length integer encoding. If it was a fixed length like 16-bit or 32-bit, endian selection becomes an issue, but if it was a variable length integer encoding, it would not be a problem. Like with UTF-8, it is an encoding that uses the first 2 bits to determine how many bits the value is going to be. Next discussion was around what to do with the streams. Whether it was HTTP2 or QUIC, it can send multiple streams concurrently over one connection. In case of HTTP2, what is sent is the bidirectional stream of the request by the client and the response are sent by the server, or push only, that is pushed by the server. In contrast, because QUIC is aiming to become a generic protocol, there may be cases where the server sends a request and the client sending back the response. Or there may be cases where the client sends something unidirectionally. As a result of this discussion, they agreed to on the need of having a unidirectional stream. When using TLS 1.3, whether the server speaks first or the client speaks first differ depending on the situation, but considering to exchange the HTTP3 setting at early stage rather than deciding whether the server speaks first or the client speaks first, they have decided that it is much simpler to faster to allow whichever that is ready to start speaking first. The next discussion was that if a unidirectional stream is available, then bidirectional stream may not be needed. If it is needed, for example, the unidirectional stream of request may be made by the application and another unidirectional stream of the response made by the server can be bundled to realize bidirectional-like stream. That was the next discussion. As a result, they have decided that as long as many applications require bidirectional streams, it would be better for QUIC to provide bidirectional stream. As a result, QUIC provides 4 streams, bidirectional or unidirectional, and whether it's client-initiated stream or server-initiated stream. 2 times 2 provides 4 different types. They have decided to use the last 2 bits to determine which stream type it is. For example, if the stream ID is 0, it is the client-initiated bidirectional stream. If the stream ID is 1, it is a client-initiated under unidirectional stream. Next, I would like to talk about connection ID. Connection ID is a mechanism to allow the server to determine which packet belongs to which connection in case it handles multiple handshakes. With TCP, client ID address and port number were used, but with QUIC, as long as there is a possibility of address change due to migration, the different identifier is required. There's a need to insert connection ID per packet, but there would be an issue of privacy if you carry the same connection ID through the network. So with IETF QUIC, they have decided to have the server and the client issue multiple connection ID beforehand, and upon network migration, it would switch to a new connection ID. And that looks like it had solved the user tracking issue in case of migration, but that was not actually true. This is the QUIC packet format. Red represent plain text. Yellow represent plain text with tamper detection. Blue represent the encrypted portion. Originally, plain text data like the red portion is built internally, and by applying AEAD encryption later, the payload, meaning the data, gets encrypted. Also, AEAD tag detects a bit error and tampering is added. On the other hand, packet flag and connection ID, the CID, and packet number, PN, are still plain text. With regards to connection ID, they have introduce a mechanism to switch to a new ID upon migration, but how about packet number? Packet number is a number that is sequentially incremented, such as 0, 1, 2, 3, 4. If you track this number in case of migration, user can be tracked. For example, if the last packet number on the Wi-Fi was 543, and if the packet number on the cellular network was 544, people can guess that these are the same user. In addition, the plain text packet number has another issue. Earlier, I talked about TCP ossification. In addition to firewall, there are many devices on the internet that monitors TCP in many ways and try to remediate issues. These include that we try to fix the packet order when the packet comes through in reverse order. By fixing the order, it would try to reduce the packet retransmission and effectively use bandwidth. However, fixing the packet order means that it would delay the packet otherwise would have been sent until the order is fixed, meaning that if there is a packet loss, the actual transport speed would worsen. This is another issue of TCP ossification. Can QUIC prevent such ossification issues? To do this, what was adopted was the mechanism called the header protection or packet number encryption. It is somewhat a complex mechanism, but the 16 bytes of encrypted payload is scrambled using an encryption key, and the result is XORed with a packet number. This way, the packet number becomes unknown to those who don't have the encryption key. Similarly, the flags bit are also encrypted. With this, the plain text in the packet would be the first 3 bits in the connection ID. The first 01 is the value which tells you that this is the quick short header packet, so has no other meaning, and so it can be plain text. But what is a question mark? Up to this point, we said encryption is good. It can preserve privacy and prevent ossification. But not everybody agrees. For the network and vendors, being able to visualize the user communication status is better to analyze failures and performance. To be more specific, they want information such as latency and retransmission for every connection. TCP was plain text protocol, so everything from latency to retransmission were visible. However, in an era where privacy is valued, this cannot be accepted, so they have decided to use encryption as the basis to intentionally design how and what to disclose as information for observation. How will this be done specifically? This is the first byte of the quick short header packet. The first 2 bits are fixed with 01. The last 3 bits will include information about the packet number length and the encryption key phase. There are 3 unused bits in the middle. The battle over the use of these 3 bits rose. There are the people who asked for more information using these bits and battled against those who argued that this would be a privacy risk or ossification risk.
So several discussions were held like this, and they decided to try with 1 bit. So spin bit. So observer on the network will use it to observe the connection latency. Client is sending the packet with the spin bit 0, and when it's received, it sends 1 packet, and server will return the values sent by the client. So by doing this, with 1 round trip, a bit becomes 0 or 1. But due to the privacy concern, the spin bit is optional feature. So some browsers and servers are not accommodating this. So, and also due to the ossification concern, with the browsers and servers with the spin bit, endpoints should send a random noise for at least 1/16 of the total connections. Next is Handshake. At the time of the connection establishment, handshake is done. In this diagram, we are showing the early handshake of the QUIC. TLS is used as black box. So after the handshake of TLS, QUIC receives key from TLS and packet encryption starts. In this method, there are two issues. One is double encryption between TLS and QUIC. TLS has a function of key exchange and encryption. And when TLS runs on QUIC, it's a double encryption. The second is complexity. After the handshake of TLS, QUIC key is handed over, but this timing is vague. So for example, when you can get the key after that, all TLS data can we transmit it after encryption at the QUIC. Depending on the timing, the counterpart probably do not have the key yet. Packet might be lost, and when you transmit the lost packet, you need to also consider this type of issue. So next game, the proposal not to use TLS on top of QUIC. So that is DTLS, that is to use the TLS on UDP. And use the DTLS for handshake. And using the common key, you can make the QUIC connection and then have a free communication. So if you are familiar with DTLS, it's a very natural idea. But counter argument is that DTLS is minor, so it's difficult to find a library. It takes time to do its own development. And also, using the different protocol for the data transmission from the handshake, it makes it difficult to build the new telecommunication protocol, which has the very good transmission control and congestion control. So discussion deadlocked. So they created 10-people design team to discuss the details. Going back to this diagram, so this is the structure. If you look inside the TLS, there are two layers. One is a key exchange and authentication message exchange layer. Second is to separate the message and do the encryption. So for each message of the message layer, the record, the key is determined that is used in the lower record layer. So TLS records is in charge of the encryption of the message and the separation. So why don't we abolish the TLS records so that the QUIC can do the frame layer and encryption can be done with the packet layer of the QUIC? That would make it simple and clean. This was the new design decided at the draft 13. So using the internal API of TLS, part of the TLS function is used for the handshake. So it's advantageous. That's what everybody thought. So after this change, the discussion progressed very quickly. So instead of using the TLS 1.3, they modified the TLS 1.3. It was all for good. Now, I would like to talk about HTTP 3. Let's review first. At IETF for the standardization, they ported the HTTP2 to QUIC. It was their plan. What became clear was that the QUIC means different things for different people. Some people believe that it's the Google's QUIC, and other people believe that it's the IETF's standard, that is the transport protocol. Or other people thought that ported HTTP on QUIC is QUIC. So this leads to confusion. So there were several proposals. So for example, call IETF QUIC as version 2. So you can differentiate from Google QUIC. Or call QUIC for HTTP as HQ. Or HTTP2 2.1. As a result of discussions, as a protocol of the transport layer, call IETF QUIC as QUIC version 1 was decided, and Google QUIC is the alpha version or beta version of that. And secondly, call QUIC for HTTP 3, HTTP 3. So transport changes from TCP QLS to QUIC, and this leads to faster speed. So this should be positioned as major upgrade. It's easy to understand that way. So let's review the version numbers of HTTP2. They are divided into two things. One is the HTTP semantics. It has nothing to do with the versions. Request and response, and for each request there is methods and URL. Response has 3-digit status code. There are various header fields, and there is a common semantics. And at the same time, there is HTTP 1, 2, and 3. How do you encode specifically the request and response are determined. So for example, inserting column between the name and value of a header. This is the spec of the HTTP 1. In HTTP 2, binary encoding is used instead. Now let's look at the functions of each version of HTTP. In HTTP 1, it uses the TCP and TLS in a transport layer. So there is no multiplexing. There is no header compression and no prioritization. HTTP 2, in transport layer, it uses TCP TLS, just like the version 1, and multiplexing is built in. And header compression uses HPAC, and prioritization is also built in. HTTP 3, the transport is changed to QUIC, so multiplexing is done by QUIC. What about the header compression and prioritization? Header compression in HTTP 3 is, well, first looking at the HTTP 2, HPAC combines static Huffman and compression using table. GQuick adopted HPAC as is. Static Huffman uses also HTTP 3. So let's look at the compression using tables and look at how it changed. Now, when you return the 3 HTTP response on the left, we are showing the static table embedded in protocol. The first response needs to be compressed. So colon status colon 200 is in the static table. So header, instead of compressing it with the static Huffman, you can just use the index number 8. And as for the content type header, the header name is the same name is available. So you can send a 31 as index, and header value, the string text slash HTML char set UTF-8 needs to be transmitted with the static Huffman compression. Next response, same with the status header and content type header and the content length header. The third response, this header is the same, but as for the content type header, the content type header sent right before, it has the same name and value. So this index can be sent. So this index is so-called a dynamic table index. And lastly, context length header is processed same as response. And pink arrow, which is the dynamic table index, this is extremely powerful.
This is an example of an actual request sent by Chrome. There are many different headers, but light blue represents the portions compressed by the static table. Pink represents the areas that can be compressed by dynamic table. Headers such as user agent, accept, cookie differ depending on the user, but do not change by request. So for multiple requests that are sent over one HTTP2 connection, being able to say that this is the same value as the last request is a very effective way to improve the compression ratio. However, there is an issue of using HPAC on HTTP 3. What do you think will happen when using HPAC and the second packet was lost? Although the third response is received, the header value is unknown. Because the second response is unavailable, you don't know the value. This would reduce the meaning of solving the head of line blocking issue with QUIC. Or as another issue, What would happen if the second request was canceled by the browser? If the second response is not delivered, even after the third response is received, the third response is left without knowing the header value forever. In order to solve these issues, QUIC decided to send the dictionary separately. The header will either reference the dictionary that is sent separately or the static table or make a simple or static decision. This is the compression image of QUIC. Table on the left bottom is the dictionary table that is sent separately. Please look at the content type header of the third response. It is referencing the value in the dictionary table. It is the same with the content type header of the second response. So registering the values that are referred multiple times in the dictionary beforehand is the uniqueness of the compression using QUIC. As a result of the design change, QUIC, the options of header compression algorithm had widened significantly. For example, with the deployment, by aggressively using dictionary, the compression ratio might improve. However, if the packet containing the dictionary is lost, head-of-line blocking will occur. With another deployment, you may try to avoid head-of-line blocking by refraining the use of dictionary. Now, next let's look at the prioritization control. This is the priority control of HTTP2. Client sends the key representing the priority. This is for Firefox. This is for Chrome. These are totally different in shape. Priority control in HTTP2 is very complex like this. It would have been nice if the client and the servers were deployed correctly. However, the server deployment can be often be random, or the client may not send the correct key showing the priority, causing the process to fail in some cases. So in the process of porting HTTP2 onto QUIC, there were people wanting to change the priority control method. On the other hand, there are people who object to this, want to reuse the code. If the deployment has bugs, should fix the bug. Our job is to port HTTP2 and not to build something new. Those were the objections. Discussion was deadlocked, but at this point, some people started to say there may be some other issues with HTTP2 priority control. To be specific, the priority cannot be changed on the server side. For example, sometimes you want to send just this image first, but with HTTP2 priority control, the format differs so much between browsers, server cannot intervene. That is the issue. So let's just revise the whole priority control on HTTP2. And so we have decided to completely replace with a more simple and extensible priority control mechanism. As the first step, only the two parameters U and I are defined. U represents the urgency out of 8 stages. 7 is the background process like file download. And of the 7 stages between 0 to 6, 3 in the middle is the default. I is the flag to show whether there's a meaning to send part of the image, like with the progressive JPEG image. This would be the request actually being sent by the browser. HTML is standard U equals 3. CSS or JavaScript will have a higher priority than that. Images have U equal 5. Software upgrade is U equals 7. In order for the server to upgrade the priority for a particular image, you just need to send the response header showing this. This is how it works. Let's go back to the HTTP function list. We were trying to build HTTP 3, but for some reason, the HTTP 2 specification was changed. Why did this happen? Lastly, I would like to talk about the behavior analysis of QUIC and HTTP 3. What do you use to monitor TCP and HTTP traffic? Many of you would say Wireshark. How about TLS and HTTPS? By setting the environmental variable called called SSL keylog file, you can have the browser output encryption key. By entering this into Wireshark, you can see the contents of the communication, and some of you may know this. What should you do with QUIC and HTTP3? This is not fully supported yet, but with Wireshark and SSL keylog file, you should be able to do something similar to TLS. However, the analysis using packet monitoring tool is actually not perfect. It's good that it is easy to use, but it doesn't tell you what is happening within the telecommunication protocol stack. For example, why the packet was retransmitted, why the connection was stalling. This sort of why is difficult to understand unless you see the internal status of protocol stack. That is why we have the log format called the QLog and visualization tool called QVis. QLog is a log format that is adopted by many QUIC and HTTP3 deployments as a de facto standard. QVis is a tool that visualizes the QLog file. Let's look at the visualization example. This is the visualization example. The arrow with comments on the right represents the data that was sent. In addition, you see values such as CWND, SRTT, in flight on the left. These represent the state within the protocol stack. By looking at this, you can understand the reason of the stall is due to the quick deployment issue or the network issue or the application. Such analysis can be done more easily than before. I have rushed through, but now I would like to wrap up. QUIC and HTTP3 is now reaching mainstream. Performance should get better, but many deployments are still rough and should be fine-tuned through the actual usage. Most of the information is encrypted, but we expect a new generation analytics tool would help. QUIC and HTTP3, as I mentioned today, are developed by people. It was not developed by one skilled engineer. I think I have been able to demonstrate that many people considered and discussed and compromised through the development. Both QUIC and HTTP3 are very human-like. So when you use QUIC and HTTP3 in the future, please remember this. Or if you find an issue and decide to participate in the discussion or in the improvement, I think the internet will become faster and more safe. Thank you very much for your attention today.